Cool. Sorry about that. That is the free Zoom. Is my screen sharing right now? Yep, cool. Okay, yes, where we were. So the way the load switch works, I think someone asked in the chat, there has to be an enable for this to turn on, and then this power will go through here. So we were at power supply to load switch. So we probe across VBAT and ground with our DMM, and we see that power is there on the input. So there is power getting to the load switch. What should we do next? Check that it's the right part. Yeah, that's a good preliminary thing to do. Yes, we should do that. Check that it's the correct AC. It is. So we looked at the label real quick. It was correct. We were really somehow we also replaced it with the definitely correct part, and it was still the same issue. But this is good. We're isolating the problem. What else could be going on in our circuit here? Where was it? Horn. Nope. God damn it. Okay. How does search like this? 1 sec. Let me find it in the schematics again. Nope. There we go. What else could be at play here? So remember, we one parameter for it to turn on was the power on the input. What else needs to be there? Check the right resistor values, caps, and fun stuff. That is so we could do that, but we realize it might take a bit too long. Wait, okay. Faulty connections. Okay, let's do this. So we check all the resistors. Let's not do that. That's a good point. If we were very lost, I think this, yeah, Matthew. But we are not going to check all the resistors just yet because that's a lot of work, and there are still other things you could check first. So let's what was it? Check the pins are all soldered down. They are. So that's not the problem, but that's a good point, Hunter. Check that it's all assembled correctly. That could have definitely been a problem. What else? What else is needed for this to turn on though, besides power here? What about the voltage input to the in-pin thingy? Yeah, that's a good point. Let's check that. So we measure the voltage from here to ground. Measure, oh my God. Measure voltage from in on load switch to ground, and it's 0 volts. FYI resistor values are hard. Yes. Yes, that was, I should have explained that, but that's the point. That's why I didn't want to measure all the resistors. But yeah, so just an FYI, I forget if this is correct, but it doesn't matter for this situation. We're just assuming that the voltage here has to be like 3.3 volts to turn this on, or to enable this load switch. But we've just found out that it's 0 volts. What do we do next? So then we got to check out the horn enabler. Yes, do you mean I'm guessing you mean wherever this goes to, which is our IO expander. IO expander, by the way, is like a multiplexer. So we use I2C to talk with it, and then it will enable 3v3 to go onto one of the channels. So what do we want to do? How do we want to approach this? Basically, what you know is that from the PCB, where the IN pin is to the IO expander is a trace. IO expander is down here, by the way. One of these guys. There's a trace that comes here. What do we want to check first? Or what do we notice? do you guys know how the IO expander, or do you more or less understand now how it works though? Chat is going silent. So let me explain a bit better then. I'm confused on how, okay, yes, let me explain it. So basically, I2C is connected to the IO expander. I2C is a digital communication protocol. How it works is there's a clock and there's a data line, and the rising edge of the clock with respect to the state of the data line will tell you a bit. And then with those bits, you can make a word and you can send messages to this IC. So the way it works is that we have all these load switches we want to enable, but there's so many pins that we can't just like assign a pin from our controller board. There's not enough. So what the IO expander does is that our controller board will talk to the IO expander over I2C, and then it will tell one of these pins to get 3v3 from the input, basically, and then 3v3 will appear on the pin. And we know that there is 0 volts on this pin. I'm just going to add another step. Check continuity between output of IO expander to, what is it called? Load switch is continuous. So we know that everything from this point, horn enable point to check where I2C is sending the check where I2C is sending the 3V. I'm not sure exactly what you mean, but do you want to look at like if I2C is functional? Like if the I2C is correct? So did we check if to see if the yeah, let's check. Let's do that check. So I don't know if you guys remember, but what step were we at? 8. 9. No. Okay, one sec. Give me a second. That's not how it's gonna work. Okay, I should expect that. Anyways, yes, so we scope the I2C lines, kind of like that image before. We use our oscilloscope, and one of these is the data, one of these is the clock lines. And can I pull out the whiteboard just for effect? Let me see. Is that a possibility? Breakout rooms? Nope, 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 nope. I guess that is not. Oh, I can annotate. So here is our scope. Let's just say this is SDA and this is SCL. When we probe SCL, we see the, why am I trying so hard for this? 3.3 volts. If this is like the 0 volt reference, we see a line that's at 3.3 volts. And then if this is the 0 reference on SGA, we see the exact same thing at 3.3 volt reference. No, stop. Okay. So does that kind of make sense? Like, you check if the I2C is talking. Yes. So, okay, anyways, that was what was just said. So essentially, scope I2C lines see that there is no communication. Cool. We know that I2C is not working, but now we have to figure out why is it not working. This is kind of a funny problem, but I'd say does anyone have any ideas what we should do now? Otherwise, I can suggest something. Check the hardware is sending the I2C signals. What do you mean by that? Do you mean like the schematics? We turned, what are we turning off and on? Let's just say we turned it off and on again like 1,000 times and it still didn't work. It's an actual issue. Check. I'm gonna assume that Hunter meant to check the hardware is sending the I2C signals, that we check our schematics. So we have our, you have that. Okay, so we have IO I2C SDA. Shoot, he made it at the top page. Okay, there we go. That's the port. When we go over here, where is it? Oh, there we go. Okay, so here is our SDA I2C. It goes to pin 13. Let's just add this as a step. 10 checked if the CB I2C pins were correct. CB's controller board, by the way, they were. So let's just say we looked at this breakout controller board connector, and we saw that SD is at pin 13, SDL is at pin 14. That was correct. And then Hunter suggested we check, of course, the, what was it? Yeah, the hardware for the SDA SEL. And then we go back to our I expander and we see if that's connected correctly. And does anyone notice anything? Anything kind of sus about this? Double arrows. They're connected. Yeah, they're connected the opposite. Good job, Wyatt. That was the problem. This is an actual problem. SDA is connected to SCL. SCL is connected to SDA. And I included this example because, yeah, big oof. Let me just write it down. Saw that SDA and SCL are connected incorrectly. Oof, I don't know. That was the problem. So anyways, I guess this is a huge roundabout way of looking at our schematics and making sure we have the understanding everything's connected correctly. And it all started from us looking and seeing that the controller board, or sorry, the output was not present, which is oftentimes how it starts off with, you know, we don't actually expect to have messed up something so simple, but that can happen. So good job, guys. That was pretty cool. What do you guys say to doing another one? But I guess that worked pretty smoothly. This is a trial period. Okay, let's put a cap on this because this has become a long onboarding to like maybe like 15 minutes, or let's do one more basically. Next problem that has actually happened is our SolarSense board. So last time, by the way, just for reference, this is an old version of power distribution, so we fixed that problem. But we had to troubleshoot to figure it out. Anyways, so SolarSense, this problem is that this is also, okay. Yes, okay, so we are trying to, okay, we're trying to read voltage measurements on our I2C lines from the MPPT. So let me just make this get big. Okay, so basically this is the SolarSense board. How it works is it takes a bunch of readings from these MPPTs. There's a really good knowledge share on solar. If you guys are interested, definitely check it out. It's kind of later and it's very long, but it's really good. Anyways, so we're expecting a voltage on this connector, and then that voltage is being read by this ADC. And then that ADC is going through an isolator, ADC analog to digital converter, one side is the voltage reference, one side is the I2C communication. That goes through an isolator just because there are different ground references at a different, and they have different potentials, so you can't use the same one, which is where you see all these divides. And then that's going to the controller board, the I2C, and we have connected our input power. So let's do this as the last example because I realize I'm over time. I had another one, but I could just write up the notes for that, but it would be a good troubleshooting process. But essentially, firmware is communicating through the I2C, but it's reading nothing. So that is the problem. Where shall we begin? Any ideas are good ones at this point. All we know is that no voltage is being read by the firmware. The minicom, which is basically how firmware debugs, I guess, is showing nothing. And our controller board is connected and we are seeing nothing. Blame programming. That's a later step. We blame firmware when we're like, sure, it's their fault. But right now, we aren't sure. Check the voltage manually to see if there is no voltage or if the test is wrong. That's a good step. Let's do that. Let me write this down. Check voltage at ADC, which is, no, wrong one, which is this guy over here, I'm pretty sure. If I remember, yeah, the ADC. By the way, I just assume that everything is populated that's required on this board for this specific, like, duck-like thing channel to operate. So, like, all the components here is what I meant. Yeah, so we check the voltage over here. That's what this test point is for. This is the voltage that reaches the ADC. And there is, let's just say 20 volts, which is expected. We connected it to a power supply with the 20 volt reference. All right, that's outputting 20 volts in this diagram over here. So we found that's working properly. What's a good next step? And while that test worked really well for us, it's good to note that, oh shoot, okay. So let's just say we actually measured at TP7. Let me write this down. Check voltage at TP7. It was 20 volts there. And then let's say we also measured the voltage at TP8 as the next step. Because it's actually like there's a voltage divider because 20 volts is a lot. So we don't input that into our ADC. I believe there's a voltage divider. Oh wait, that was above. Oops. Let me just remove this and let's call it not 20 volts. There is a 2 volt. I'll just say 2 volt for now. But anyways, all that means is that the resistor voltage divider is working as well as we probe here. So yes, okay, cool. So here the input to the ADC is good. What else can we check about this ADC? Let's pull it up in the schematics. So we get our vsense in, that's going good. What else should we check next? What is testing it and getting no reading again? Is that a question? Like, wait, what do you mean? Like, are you asking about the problem? Okay, yeah. So there's essentially like so we have placed our controller board on we have populated everything. We did a quick check to see if everything was connected correctly. Let me emphasize quick. And then we put a controller board on, which has our MCU. How firmware works is that they have a terminal that will show up as we connect with this jumper header over here to our laptop. And then it'll communicate with us different readings from the MCU. So firmware has code that will tell the MCU, so our STM32 microcontroller, that it has to read voltage, or actually it has to specifically communicate to I2C, to this ADC, and read the voltage it's reading. Or basically the ADC will tell it what voltage it's reading, but it's supposed to do that and then report that back to the terminal we see on like firmware team's computer. But firmware team is seeing nothing. And maybe to be a bit more specific about what the nothing is, they aren't able to communicate with the ADC because the ADC, like the way I2C works, is there's an acknowledge in the, no Siri, stop. There's an acknowledge in the, God damn it. Okay, there is an acknowledge in the first word that's sent in the data line. So when the controller board asked the ADC, what's up, it got no response at all. So that's exactly what happened, if that makes more sense. Check there isn't faulty connections between CB and ADC. Okay, that's a good point. What exactly do we want to check though? Like what connections? And I can go back to our schematics. What do you want to check? Okay, I'm going to assume what you meant by that is that you want to check if this trace ADC SCL4 reaches the controller board, or actually, where does it go? SCL1, 2, voltage sense, I forget, this is old, solar sense. Yes, okay. Okay, this is a good point, let's do this. Check if SDA and SCL reach controller board. Basically, they do. So what we checked is we did a continuity check with our multimeter. We saw the ADC. We probed this pin 8, and then we probed this isolator, and it was a good connection. And we did the same with SCL. And then from this isolator, we probed SCL and SDA to the controller board directly, and it was also a good connection. So that's a good thing to check, but that's not the issue. Let's think of it this way, though. So what else? Okay, what else? Actually, yeah, that's all we have to look at. So we see that, let's get the PCB. We see that they're connected correctly. Is there anything else you want to check about the I2C specifically, or about anything to do with the ADC? Okay, then I can suggest a direction. Let's say we just decided, you know what, I2C is connected correctly, but for some reason we're not getting a read back. I'm going to scope out the I2C on my oscilloscope and try to decode it and see what's happening. What was it doing? Okay, yeah. So I look at my I2C. I look at the scope output, what I see for my SDA and SCL is that if this is a 0-volt reference, this is a 0-volt reference for the SDA. I'm seeing the actual output is 0 for SDA and 0 for SCL. So they're both 0. Even when firmware is trying to communicate, they're both 0. And that should be a real big no-no for us because the way I2C works is that there is a pull-up resistor to each of these pins. So if the component wasn't working, it should still show, like, from the previous problem, just 3v3 on both those lines because there's a pull-up resistor, which means there is a resistor connecting to 3.3 volts and pulling up the line. So even if something wasn't working, it wasn't pulling down the line correctly, it should show us 3v3 like it did before. But it's not. So that's a good problem to find. Now you have to figure out why. Scoped I2C and saw 0 volts on, okay. So 0 volts on lines. Cool. So now that we know it's 0 volts, we have to figure out why. What could possibly be an issue for why this isn't actually connected to 3.3 volts? How about this? Remember when I was first, like, in the preliminary checks we have, we want to, I don't know if I actually added this at this point. I explicitly check power rails, check. Yes, what are some of these preliminary checks we can do or identification we can do on the board? Or better yet, okay, let's look at, I think it's a good idea at this point to look at the power rails, because if we're not seeing 3.3 volts here, or 3.3 volts here, what are we seeing here, right? So let's just say we probe 3v3 in ground. Where did it go? Here it went. Probed 3v3 with respect to ground, 0 volts. Oh, that's strange. Why is 3v3 not working? What could possibly, like, I realize you guys haven't really troubleshot before, but what do you guys think could possibly be a reason 3v3 is not working? Or it's the same reference as ground. Check the power supply. That's a good idea. So the power supply in our case is the controller board has a regulator for 3.3 volts. So let's say we take off controller board and probe 3v3 on it. When we do that, we see 3v3. So essentially, we removed the power supply from the board, we probed it, and we saw there was still 3.3 volts. Specifically, we took off this guy, and there's 3.3 volts there. But when we put it back on, and we measure the 3v3 trace, we see 0 volts. So what could that mean for us? Okay, well, I'm just going to say it. That means there could possibly be a short, which is what we're going to check for next. So we see our 3.3 volt trace. We take off our controller board just because if there's a short, you don't need the supply to tell you that, and you could possibly blow a fuse on your multimeter in a different situation. But anyways, we take off the controller board. We measure the resistance with our ohm meter from 3v3 to ground. Measure resistance between ground and 3v3. And we see there is almost zero resistance. And what does that mean for us? There's a short. There's a short. So what that means is that we've now figured out that there is somewhere on our board, there's ground and 3.3 volts connected to each other. Check the soldering for the short. That's the best next step. So check connections for short visibly. Don't see any, but okay, I'll tell you this, because of the way this board is and how big it is and how much there's going on with the 3.3 volt trace, there's a lot of things that could possibly be the issue for the short. And this isn't like a complex problem or anything. This is the actual problem is actually very tedious to isolate because the short is somewhere that's not that clear. So what we want to do now is take off components from 3v3 until short disappears. So what we see here is that, I'll tell you what the output is in a second, but what we see is that there's so much on this board that's connected to 3. There's a possibility the component is the issue. There's a possibility that there's a solder joint. From our visible checks, there wasn't anything too obvious, but the best way to really isolate it is start taking things off. And you'll find that that's actually, that has to happen so much more than we'd ideally want, because sometimes the shorts are just not detectable. And based on the quality of the fabrication, it could be, wouldn't that take like forever? Yes and no. Yes, it would if you just randomly took off all the components. No, if you kind of thought about what could possibly be the issue. Also, yes, if it's a problem you've not seen before. So I'll cut to the chase, because when I was debugging this, it actually took a really long time. But it was basically the way this was manufactured was not ideal and could have been the tolerances as well. But there was like a small short between 3v3, this pin, and the ground plane, because some of the solder mask scraped off and the solder was connecting. So I essentially had to take off all the components until U2, and then see that short disappear. So yes and no, that could take forever, but that could be a problem. So yeah, that's a less big brain solution to our problems, but that's an actual issue. So take off U2 to see short, go. And then the way you would basically proceed from there is make sure that the short, or basically scrape off the connection from the short to the board, solder it down better, see it go when you put this back, and then put everything back on. So what's the manufacturer's fault? Well, in this case, I think it was a bit of both, a bit of the tolerances I put on the board. So like the space between the copper and the non-copper region. So like when you have a trace, here's your ground copper, here's the copper trace. This like dark green is like the distance between. And for this pin, like at a specific point, it could have been a bit better. But it was also that we decided to cut, well, it wasn't really cutting costs, but we got it from a manufacturer that I later realized was like made pretty shitty boards. Like the solder mask, you could scrape off with your finger. So it's a bit of both issues. But that is it. We figured it out. It's a very roundabout way of figuring out a 3-3 short, but sometimes that happens when you don't expect that to be the problem. Cool. And I had another problem, but this took way longer than I expected. Well, I should have expected it to take this long, but I will. Yeah, it's very annoying. It is. Troubleshooting is fun because it's kind of like puzzles, but it's also not that fun when you realize it's something stupid. But to end my presentation, here's some useful resources both online, and every time someone on our team does troubleshooting, we usually like to keep a page that records everything we've worked through. So you might see some of these examples in the Confluence documentation we have. And we try to learn from that, because oftentimes you'll like, you know, with the 3v3 thing, you'll take off everything and then still not find the problem. And then you'll like be like, what the fuck? Where is it? You know, but you'll have a better record of everything you've done with the documentation, which is why it's really important to keep consistent documentation through your validation. But yeah, that's it for me. That was kind of long. Do we have any questions at this moment? And we have about 1 minute. Thanks. Yeah, I'd love to hear feedback later of all the onboarding. But for me, I just want to know how chaotic the last part was. But yeah, we are done. Winter 2021 onboarding. And hopefully when we're all back in the Bay or get a chance to be in the Bay, you'll get to actually troubleshoot and learn about the frustrations or have a fun time. Never know. It's a bit of both. But cool. If there's no other questions, I think we'll end it there, or Zoom will kick us out in any case. So thanks, everyone. And bye.